Hi, welcome to this video in which I will be explaining the new chapter about sets cardinality. The outline is actually three different parts: the definition of cardinality of sets, and then we will see that cardinality can be a finite number, so the size of a set can be a specific integer. In this case, the set can be finite. Otherwise, it would be an infinite set. But here we have a tricky classification of those infinite sets. So we have countably infinite sets and uncountable sets or uncountably infinite sets. Okay, so let's start with the first one, the definition of cardinality of sets. Set cardinality designates the size of the set. So maybe we discussed it during the session about sets, and we define it as the number of elements in the set. For example, those beautiful creatures form a set of three different elements. Okay, so the size of the set in this case is equal to 3. In case you have a set called A, you denote the size of A with double vertical bars to the right and to the left to the set name, as if you were designating an absolute value. Okay, so we did the size of A in this case. Well, what if we actually sorry, so how to quantify the cardinality of sets or the size of sets? So two sets are said to be equipotent or equinumerous if there is a bijection between them. So maybe you still remember the remark with which I started the last session about functions. I said that one of the applications of functions is to reason about the size of sets or the cardinality of sets. So actually, maybe you still remember that an injective function has a constraint on the size of A and B. You have another constraint when the function between A and B is surjective, and you have both of them. The constraint must be met by both sets is to have an equal set, equal size. You cannot have two sets of different sizes and still be able to define a bijection between them. So if it is a function at the first place and the bijection, then clearly those two sets are of equal size. Of course, once you can define a certain bijection, maybe you can define others. But if at least one bijection is definable between those two different sets, then clearly they have the same size. Because every element here has one exact image in the codomain, and every element in the codomain has exactly one preimage in the set, and all of them have exactly that image or preimage. So they must be of equal size. It's an equivalence mapping between those two different sets. So here you have a couple of examples about functions that are bijective. So actually, I like the other example with the currency. Well, here, if you add an additional country to your set, but you do not add the corresponding currency, the function is not, you cannot define actually a bijection between these two different sets. But regardless of the semantic of the um, function, actually, is just unfeasible. You cannot come up with any function, whether it makes sense or not, because simply the number of elements in the first one is different than the number of elements in the second one. Okay, so whether the domain is greater or less than the codomain or vice versa does not matter. If they do not have the same size, then you cannot define a bijection. Well, in this case, you will see that for finite sets, we have a trick to prove the set is finite using bijections, and we need this concept also to prove properties about infinite sets, although the ideas might become trickier when talking about infinite sets. So let's check how to prove that a certain set is finite. Actually, if you succeed in defining a certain a threshold n, and in defining a bijection f that maps every natural number between 0 and n, it means from 0 to n minus 1, to every element in S. Once again, it's a bijection, so every number here has been mapped to every element in S. Then in this case, you can say that your set is finite, your set S is finite. Let's visualize this. Actually, your function f would have mapped the integer 0 to a certain element from S, which is 0, okay? Let's call it S0, a certain element in the set S. So we're considering elements from the set N, actually not all of N, I'm sorry. So just the set from 0 to N minus 1. And we are mapping them to elements in S, okay? So in this case, f of 0 would be a certain element, let's call it S subscript 0 in the set S. F of 1 would be a certain element, let's call it S1, and so on and so forth. If this mapping is a one-on-one mapping and on-two mapping, then clearly there are no other elements left in S without any pre-images in this set here, and vice versa. So clearly, these are all the elements in S, and defining this bijection, it means that you succeeded in counting actually, or enumerating or listing all the elements in S in a finite way, okay, after n steps. Good. So just if you're wondering why we stop at n minus 1, please remember that if I want to count the number of those elements here, so it's n minus 1, the last index, minus the first index, which is 0, plus 1. This is the rule. And this actually gives you n. Okay, so this is why we have n elements here with n. This is starting from 0. So you can check it on your own with a few examples. Well, in this case, the cardinality of S is n, and we write that the size of n, or the cardinality of S, is equal to n. When the set is S is equal to the empty set, then by convention, we suppose that n is equal to 0. Actually, the size of the set is equal to 0. Okay, so although this does not fit with this definition above, but we still admitted by convention to have a coherent results. A set is infinite actually if it is not finite. It means if you cannot find such an n as above. Okay. Well, in this case, you have two different possibilities. You may have a countable set or uncountable set. I will go over the definition very quickly, and then I will dedicate two other small videos for countably infinite sets and for uncountable sets. So a set S is said to be countably infinite if there is a bijection F that maps every element in the set of natural integers starting from 0 and all the other positive integers to your set S. That is, we are able to enumerate or list all the elements of S as follows: as 0, as 1, as I did on the previous slide, but simply this goes on and on. So you have a certain function that magically maps actually every single integer j to a certain element as j in your set n. In this case, we must say that S and n have the same cardinality, and we know that the size of n is infinite. Yet it's a countable, countably infinite set. Okay, so why it's countable, enumerable? Because actually, um, between any two different elements, let's say between S0 and S1, there are no other elements in there. Okay, so you can talk about the first element of S, the second element of S, the third one, and you don't have anyone in between, and so on and so forth. And the kth one, like any SK, okay, and so on and so forth. So there is really a one-to-one mapping, a bijective mapping between every single integer and your elements in your set, okay? So you give me k, I would calculate f of k being sk, okay? Subscript k. So actually, this ability to go to the infinite, but in only one direction, okay, is what we can call countable infinity, enumerable. So you can really designate in a discrete way all the items in the set, all the elements in the set. Okay, like sometimes they talk about an imaginary hotel that actually has no fixed number of floors. It simply can go up um, with additional floors as much as needed. So each time you have a new guest, you can simply build a new floor on top of that hotel. Okay, so you can always accommodate new guests. Okay, but in this case, you still have floor number 0, floor number 1, floor number 2, and so on and so forth. So you can talk about every single floor that you have. And if you have additional guests, it's fine. You can build new um, floors and accommodate new guests. Okay. Um, well, how this compares to uncountably infinite sets or uncountable sets? Well, when you cannot define a bijection between S and N, then the set is uncountably infinite. And if you get back to this hotel example, it means that besides those floors that you can add on the top, um, you have a special case where between F0 and F1, okay, so you can just push F1 upward, F0 is here, and just you can throw something in between, maybe F0.5, okay, because we are used to real numbers. So actually, you can add as many floors as needed between any two different floors. So it goes infinitely in this way, or you can also see it as certain side floors that you can add to the right and to the left. So it's not only one single direction of infinity. Okay, so and once again between f0 and f0.5, I can also add a new floor. I can push everything in between. Okay, so well, this infinity is, if we can say, kind of like bigger than this infinity, and I cannot enumerate my numbers. It goes indefinitely. Okay, so anyone can challenge me and can come up with f 0.5000000001. Okay, and another one would challenge him or her and come up with another number in between this number and its next number. Okay, so here we have something similar to the infinity of the set n. We have countable items. It's infinite. We can always talk about a bigger number, like come up with whatever number that you know, 10 to the power, whatever you want, and then I can come up with that number plus one. Okay, this is the definition of natural integers. Every number n has a successor that is equal to n plus 1. Okay, and using this notion indefinitely, I can create this like infinite set, yet it's countably infinite. But with R, actually, we don't have this notion. So for every real number R, what you can add to it, that epsilon that you can add to R, like it can be any uh, infinitely small number, and you still get you don't get actually to that next element. I can always beat you and come up with another epsilon prime between less than epsilon, so that r plus epsilon prime is the best candidate to be the next element to R, okay? But you can beat me again, and it never stops. So we have this double dimensional um, um, growth upward and in all the direction between any two different numbers. And here we have a kind of a discrete sequence of innumerable elements, but here with the set R, it's actually we have a continuum in this case, and the size is actually an uncountable infinity actually. Okay, so more about those two different concepts will be given to you in separate videos.